So last video we figured out how to find the gradient of any point of this graph y equals x squared. We found that to be 2x, and I've written it down here. Gradient equals the change in y over the change in x, and that we found to be 2x. And that's for a general point. So for any x value that corresponds to a y value on this curve, we can find the gradient of that point. So the gradient at x equals 0 is just going to be 0. 2 times 0 is 0. And let's check that. That seems about right to me. It's at the origin, so the gradient, the tangent touching that point would have a gradient of 0 because it would be a flat line, and we know the gradient of a flat line is 0. Okay, so from this we can derive our most important rule at this level for differentiating functions. So what has happened here is we have gone from x squared to 2x. And the way that this works, in order to find the derivative, which is this here, this gradient function, so to speak, is to subtract 1 from the power and multiply the original power by the number in front of the x function. So we bring that 2 down, and we multiply by it. And let's check, let's see if that's worked. So the original power on top of the x was 2. We've taken away 1, and we can see that the power there is in fact now 1. What about the number in front of the x? Well, originally there was a 1 in front of the x squared. We've multiplied by 2, and so now it becomes 2x. And that is our general formula, so to speak, in order to find the gradient or the derivative of any y equals x function. So we can represent that generally. We can have kx to the n. So n is the power, k is the number in front of it. And let's find the derivative of that. Actually, let's call that y equals. And so, last video you might remember that we talked about using the letter d as a small difference. Another way to write this gradient, or the change in y over the change in x, is dy dx. That tells us the derivative, which is also the gradient of the function. So dy dx of this here, well, let's times down the power. So it would be k times n multiplied by x n minus 1. So that is the general form you're going to use for finding the derivative of a function. Let's put that into practice. Let's give you an example of what a question might look like. So let's move on to our graph here. Let's draw something that looks like this. And we can call this y equals x to the power of 3. Okay, so this is our new function, and I want you to find the gradient function of a point on this graph. So let's find the derivative. dy dx of y equals x to the 3. So let's multiply down the number. 3 times the 1 in front of the x will give us 3. And take away 1 from the power will leave us with x squared. Let's try that when there is a number in front. So instead of y equals x cubed, we could have, change color, we could have y equals 2x cubed. The rule is exactly the same. We multiply down the power, which would give us 6x, and subtract 1 from the power would leave us with 2. So for any point on this graph here, I can now find the gradient of that point by plugging in the x value into my new function that is for searching for the gradient. Let's have a look at what happens now when we move our graph upwards by 5. Here I have the graph of x squared plus 5. So now you'll be thinking, well, this curve looks exactly the same as the last curve that we saw, y equals x squared, except it's been moved upwards. So in theory, nothing should have happened to the gradient, and you'd be right. At this point, the gradient is exactly the same as y equals x squared. Let's say at this point here, where x equals 2, the gradient would still be 2 times 2, which is 4. So you can see that the gradient is unaffected by a constant. This means that when we differentiate a function, the constant goes. So any number, any constant in the function disappears, and only the parts with x's in actually matter. So the differentiated function would look like this, 2x, exactly the same as the one before, which was y equals x squared. Okay, so now let's look at another function, this time with multiple parts. So say I had y equals 2x cubed plus 4x squared minus 5. So we know that this constant here, this constant must just disappear. Let's look at this first term here. We have the power of 3, so let's times that down with the 2. That will give us 6. X, take 1 from the power, leaves us 2. Our second term, let's multiply down the power, so that's 4 times 2 is 8. Take 1 from the power would leave us with the power of 1, so that's just 8x. And there we have it. We have a new function that tells us for every single point on this function here what the gradient is going to be. Now this works for all, or if not most, functions. They can get more complicated, but the most common type of function you'll see is this type here, where they have powers of x's and constants, etc. Now these numbers could be anything, but also you might come across something that looks like this. So we have y equals 5 over x squared. Now this looks a bit different. Do we just multiply down the 2? Well, no, because let's think about the rules of indices. What does this actually equal? I suggest you give this a go first. So let's have a look. We have 5x. We know this is on the bottom of the fraction, so the power there must be a minus 2. Okay, so now this is in a form that we're familiar with. This is the kx to the n. Now we can differentiate it. So the same rules apply. We multiply down the power. And so that would be minus 2 times 5, which would be minus 10x. And then this power up here, we subtract 1 from it. So what would that be? Minus 3. So as you can see, it works for negative powers as well. What about fractional powers? Well, let's give it a go. Y equals half x to the power of 3 over 2. We can differentiate this really easily. Follows the exact same rules. It's in the correct form. Here we have kx to the n. So let's differentiate this one as an example. Multiply down the power. That would be a half times 3 over 2. You can do a better 2 than that. 3 over 2. X to the power of 3 over 2 minus 1. Now what does that come out as? Well, we can do that. Multiply the fractions. 3 over 4x to the power of a half. Now hopefully that made sense, and those are just some of the examples of questions that you'll come across while differentiating.